going to go to length constant. And length constant is just going to be the distance that you can travel before you reach 2/3 of your original voltage. So to give it numbers, if you started out with 1 volt, your length constant would be the length that you could travel before you got to 0.63 volts.
Okay.
So basically, like, this is my axon, I'm traveling along. If I start out with 1 volt right here, and I get to 0.63 volts right here, this is my length constant.
Gotcha.
Okay, and so the way that that's applicable is with larger, your length constant depends on internal resistance. So this is dealing mainly with the size of neurons. So if you have a really skinny axon, then there's going to be a lot of internal resistance. When there's a lot of internal resistance, you're not going to get as far before you dissipate. Whereas if you have a really massive axon, comparatively speaking, you can get a lot further before it dissipates, because you can take the path of least resistance in the smack center, and there's not as much internal resistance in a large axon as there is in a small one.
Okay.
So that means that if you have a large axon, you can travel further without losing your charge.
Okay. So it's depending on the actual size of the axon.
Mm-hmm.
Gotcha.
So based on both the length constant and your time constant, that's how you get that the larger your axon, the faster you're going to have conduction. And also, if it's myelinated versus unmyelinated, the myelinated is always going to win. It's going to be faster. And so a large, fast myelinated is going to be faster than a small myelinated.
All right.
Okay? Okay. Next thing we're going to do is we're going to go through skeletal muscle. And so we'll just start up here with our neuron and then go from there. So with skeletal muscle, acetylcholine is involved. So you have an action potential in your neuron.
Mm-hmm.
So the depolarization, which I'm going to abbreviate to DEP, travels down the axon to the axon terminal. When it gets down here to the axon terminal, the depolarization is going to cause voltage-gated calcium channels to open. And calcium is going to come in.
Depolarization causes voltage-gated calcium channels to open, and calcium can come in.
Okay. So when the calcium comes in, what calcium does is it causes all these synaptic vesicles, which are basically these little pouches that have acetylcholine in them, to fuse with the membrane. And then that's released into the synaptic cleft. So the vesicles are made out of the same materials that are in the membrane. So basically they just like come up close to it, fuse, and then it dumps its acetylcholine out into the cleft. And depending on how much depolarization you have, is going to determine when your calcium channels close.
Mm-hmm.
And so you can release one little packet of acetylcholine. That's where you would get a twitch. or you can release a lot and keep releasing it. If the action potentials keep coming down, that's when you're going to have a sustained contraction or a tetanus.
Okay.
Yeah.
Awesome.
Okay, so this is your motor end plate, where on your muscle and on the motor end plate you have nicotinic receptors. So like I showed you earlier, the nicotinic receptors are going to come bind, or the acetylcholine is going to come bind to the nicotinic receptors, and that's going to cause potassium to go out and sodium to come in. When the sodium comes in, it's just like if it were in another neuron, you get a depolarization. Okay?
Okay.
So this is what's happening at the synaptic cleft. This part in the middle is called the synaptic cleft. This is the synapse between the muscle and the neuron. So then that takes us to the T-tubules, which I don't really know what they look like, but I'm going to draw it like this. The depolarization travels down the T-tubules. And if this is my sarcoplasmic reticulum, it's going to go open voltage-gated ryanodine receptors. And then those are going to spit calcium out into the muscle cell. Okay?
Okay.
Then we're going to go to like a sarcomere level. You have your sarcomere, and it has, let's see, you have your actin and your myosin. On the actin, you have troponin C, which I'm going to mark with a C. The calcium comes and binds to the troponin C, which causes the conformational change that twists the tropomyosin out of the way and exposes the binding sites. And then the head on the myosin is just going to reach up and attach to the actin, because that binding site is open, and anytime that binding site is open and it can get it, the myosin is just going to reach up and attach. Okay. To get this myosin to unattach, you have to have ATP. So the ATP comes in and binds to the myosin and breaks it free. So that sounds kind of counterintuitive. You would almost think that the ATP would be needed for it to attach. But if you think about it, you have to have a force to break something loose. If you want to break a leg, you don't generally want to, but if you needed to break that bone, you would have to have a force. So the ATP is providing the force to break the head off of the actin. Okay, so when you have the ATP, it comes back down. The ATP is hydrolyzed to ADP and then phosphate. And so after that happens, you have what they call the power stroke, where it's come down and now it's going to shift back to a new location. So we're going to draw it a little bit bigger. This is what it was like earlier. The ATP comes in and binds, and it breaks free. And still has ATP on it. And then you have this going to ADP plus phosphate, and it's going to shift this way. It's going to do a power stroke. And then the ADP is going to leave. So ADP leaves. And as soon as there's nothing attached to it again, it's going to reach up and grab the actin again. The actin cannot be bound to the myosin if it has ATP or ADP attached. It's only attached to the myosin when it is naked.
So one more time about the can't.
Okay, so whenever the myosin is attached to the actin, there's nothing bound to it. There's no ADP, there's no ATP. ATP breaks it loose, and basically it uses that energy it uses the energy to break it loose. And then because it used the energy, it breaks apart to ADP and phosphate. And then the ADP just really isn't keen on hanging around, so it leaves. And when it leaves, it reaches up and it just holds on again. But it holds on in a different place.
Okay.
The power stroke, what it does is it moves to a different location.
Gotcha.
So if you have a tetanus, what you're going to have is you're just going to have constant pulling. You're never going to relax. But if you have just a regular muscle contraction, eventually it's going to end. So that's where your circa pump or your calcium ATPase comes in. The circa pump is right here, and it's going to use ATP to bring the calcium back into the sarcoplasmic reticulum.
Gotcha.
Okay, and then when there's no calcium left out here, it's not bound to the troponin C. The tropomyosin moves back up and covers up the binding spots, and you can't contract anymore. So there's two ways to end contraction. You can either get rid of the calcium, and then the binding spots aren't open, or remember how we talked about the myosin ATPase? What the myosin ATPase is it changes some of this ADP back to ATP. If you don't have that, then you'll run out of ATP and you can't ever break it loose. So that's what happens in rigor mortis. When people die, eventually their cells quit making ATP. And then if there's no ATP to break this loose, you're stuck frozen where you are.
Cool.
Okay, does it make sense?
Yeah, that was great.